Hello, good morning, DevOps Poland. You're good? Excellent. This talk is about software architecture, and this talk is also about code. And this talk has basically been inspired by questions like this. Does anybody have any recommendations for drawing pictures that's not Visio? This is a kind of standard question I get asked all the time. So who am I? I'm Simon Brown, and I live in Jersey and Channel Islands. Can you all see Jersey on this map? No, it's way too small. If this was a huge iPad, we could pinch to zoom in, we get a bit closer, and we could pinch to zoom in again, and there's Jersey. So it's a small island, 9 miles by 5, surrounded by sea, 100,000 people. Why on earth do I live there? Basically, it's a nice place. That's it. Over the past few years, I've been gesturing around the world and really helping teams understand what software architecture is all about. And my whole kind of unique pitch here is that architecture needs to be much more accessible to us as software developers. If anybody's tried to read any of those classic architecture books, the really big, thick ones, they're fantastic books, but they tend to be quite hard to understand. How do you take the content in those books and map them to your day-to-day work, for example? How do I fix this problem? I write my own book. That obviously seems the way to fix the problem. So as a thank you for coming along, I'll throw this code up at the end, and you could buy my book at a discount. I still do write code as well. And that's important because software architecture and code, I think, are basically two sides of the same coin. And what I'm really interested in here is the intersection between the software architecture world up here and the code world down here. And specifically, I'm interested in how we can communicate, visualize, and describe software architecture. But there's a tension between the software architecture and the code. So let's just have a look at that very briefly. Imagine you are trying to visualize and describe a software system that you have. A good way to do this is with pictures. But it's really hard to show everything on a single picture, isn't it? So what we do is we have different pictures to show different things. This is the whole concept of views and viewpoints and perspectives that you read about in many of the architecture books. This is from Philip Cruikshan's 4+1 architectural model. And he basically says this: to describe a software architecture, we use a model composed of multiple views or perspectives. This is Philip Cruikshan's 4+1 model. Top left, a logical view. So we somehow create a representation of our software based around logical modules or components or services. We have a development view, which is much more about the code and the structure and the organization of the code. We then have a process view, which is really multi-threading and concurrency and all those sorts of things. And then there's a physical view, which basically says, how does all that stuff map onto real infrastructure? And all of these are tied together with a bunch of use cases. This is one approach to describing software architectures. There are lots of others, but the common theme across most of them is this. You see, the logical view is separate from the development view. So we're kind of creating this artificial separation between these two worlds. I run workshops all around the world, and I teach people how to draw pictures, which kind of sounds crazy, I know, but I jet around, and one of the things I do is I give people some requirements, and I say, here's some requirements, go and design a solution, and draw some pictures to subsequently describe that solution to me. And people really struggle with this. I'll give you some examples. This is a real diagram from a real workshop a few years back. People like to draw me a functional view of the system, and it's basically just a bunch of boxes with things in. Imagine you're having a house built, and you ask your building architect to draw you a functional view of your house. Eating, sleeping, entertaining, yeah, it's just useless. I like people on my diagrams because people add context as to who is using the system, but let's give them a name, otherwise they're just faceless clones, they're stormtroopers attacking your system. This is quite apt since we're in the Star Wars room. Do you like this one? This is just a crazy, crazy diagram. The central spine represents a bunch of steps in a workflow, and then it just goes completely bonkers. So on the right here, we have this blob, this green blob, and this green blob's important because everything's pointing to it. It's like Amsterdam Schiphol or London Heathrow. It's a big airport hub. On the other side, It's just different colors, shapes, lines, types of lines. That box there says UI, user interface, upside down. Do you know why? Because people were sitting around a rounded table and just scribbled from wherever they were. This is just too boring to be useful. Here's the system, and inside our system we have auditing stuff, and we generate some reports, and we handle errors, we have a scheduler, and in the middle, we do business logic. Wow. This describes like every single system I've ever worked on. You've heard of POJOs, plain old Java objects? Well, there's a homeless edition that nobody tells you about in the books. This diagram here shows a SQL Server database at the bottom. So this is a C#.NET solution. And up the top, there's an application box. It's labeled console C#. It's a public static void main style app. What's everything else? We've got a bunch of boxes all labeled C#. They're just homeless objects kind of floating around next to a database somewhere. It's a really weird diagram. This one here is like those books I used to have when I was a kid, Choose Your Own Adventure. You'd start from page 1, you'd read through 10 or 20 pages, and you get to a fork in the story. And you as the reader get to choose which way you go next. Do you battle the big dragon, or do you run away like a coward? This diagram's the same. You start at the top, and you go down, and you get to make some choices. So this diagram is showing an asynchronous event style of architecture. Fail events, complete events, reject events. Lots of different paths through this architecture. When I read these books as a kid, my character almost always died, which is really annoying. This diagram's the same. If you look at it for long enough, you will also die. Why? Because all paths lead to the trap. It's all one color. There's lots of stuff on here. There are very few tech choices. For those of you who are laughing, this is basically a microservices architecture. This is what we will be building in like a year's time. What's the purpose of these diagrams? If I'm drawing these pictures during an upfront design exercise, then it's this question. Here's a diagram. Is this what we're going to build? If I'm drawing diagrams retrospectively for an existing system, then it's that question. Is this what we have? Is this how we actually built it? Now, when we're drawing these diagrams, we're using abstractions. So let's set the scene. Imagine you inherit a Java code base, and it has 100,000 classes. And somebody asks you to draw a diagram to describe that system. Will your diagram include 100,000 boxes? I hope not, because that's going to take a very, very, very long time to create. But what we do is we group these classes together into modules, or components, or services, or layers. And we use these abstractions on our diagrams. So abstractions allow us to reason about a large or complex software system. And that's good. But do these abstractions reflect reality? In other words, can we see these modules, services, components, and layers in the code base? Who thinks this is true of their systems? I can see one. This is really common, though. So we have a bunch of architecture diagrams on the wall, and the diagrams don't quite reflect the code. So what's the purpose of having the diagrams in the first place? Why does this happen? Well, it might happen because our diagrams get out of date. Let's park that category to one side. It also happens because we're thinking in terms of different things. So when we're drawing our architecture diagrams, we're drawing components and modules and services and layers. But these things, these concepts, don't exist in Java. There's no component keyword in Java. There's no layer keyword in Java. We have to create these abstractions based upon interfaces and classes and packages. So the two worlds don't meet. Layered architectures. Yes, we normally adopt a layered architecture. What's a layered architecture? Imagine we're building a web app. We might have a bunch of controllers, web controllers, we might have a bunch of services, and we might have a bunch of data access objects. This is a fairly standardized pattern. And what we like to say is, well, each layer can only talk to the layer below it. So we like to put some rules in to hopefully help us create a nice, clean architecture. We all know how this pans out, don't we? So we have feature set A, feature set B, and we need to add C. And C needs bits of A and bits of B. What do? Probably something like that. In Java, what we normally do is every layer becomes a separate Java package. And in order for the layer above to call stuff in that package, we make every class public. And once every class becomes public, you can call them from anywhere. And that's why we start out with this nice intent of having this nice, strictly layered architecture, but over time it just evolves into a big ball of mud. Ports and adapters, hexagonal architectures, these are essentially just layered architectures as well. Sometimes the arrows point the other way, sometimes we move the interfaces into a central domain package. It's still essentially a layered architecture. A layer is important. Why do we do layers? Well, separation of concerns, mocking, makes testing easier. We can use dependency injection. There are a bunch of reasons that we use layers. But are they important? If you look at a code base, should we be organizing our code by layer as the primary organizational structure? Or are layers just an implementation detail that we really shouldn't care too much about? We can slice and dice our code another way. So we can use a package by feature approach. So in other words, we have a single Java package, and everything related to feature set A sits in that package. Does this solve the problem of messy code bases? No, it's just a different way to structure the code. The same thing happens if you want to add a new feature that needs bits of A and B, you get into the same sort of mess. So what this is basically about is the organization of the code versus those architectural views. And these are two different things, and we think of them separately. Modules and components and services, and packages and layers and things like this. Now, this is not a new problem. A friend of mine, George Fairbanks, has got a fantastic book about software architecture called Just Enough Software Architecture. And in his book, he talks about the model code gap. So in other words, there's a gap of understanding between the model of our system, the architecture, and the code. The model is all about abstract constructs like modules and components and services. But in the code, well, that's code. It's packages and classes and interfaces. Let's backtrack 1 second. It's 2015. Why am I still drawing architecture pictures by hand? These diagrams will also get out of date very, very quickly. So why don't we just auto-generate them? Right, we have a code base with 100,000 classes. Why don't we just auto-generate some pictures? Has anybody tried this? Do you know how much of a mess it looks? Yeah. Basically, you point these tools at your code base and say, draw me a picture, and it just goes, it just basically tells you you have a mess of 100,000 classes all coupled together. I know that. I don't need a picture to explain it to me. But these diagramming tools, why do they do this? These diagramming tools also suffer from the model code gap. These diagramming tools, the static analysis tools, they don't understand what a module is. They don't understand what a layer is, what a component is. We have to teach these tools what these constructs are. And that's why we get pictures that look like this. And they often have lots of class names in. And I'm not sure I'm really interested in classes when I'm drawing software architecture pictures. Right, so that's a little bit of background between the tension, architecture versus code. Let's first of all solve the problem of how we should describe a software system. And then maybe some other stuff will fall into place afterwards. If you look back at our industry, we've got the unified modeling language. Right, quick show of hands. Who uses UML here? This is going to be fascinating. It's a very, very small number. I think probably less than 10%. And that's a fairly common sort of percentage. UML gives you a standard set of abstractions and a standard set of boxes and lines notations to represent those abstractions. And when I see people using UML, they normally abuse both. So for example, I've seen people using UML class diagrams to basically draw boxes and arrows pictures, because a class diagram is boxes and arrows, but the boxes are not classes. Let's push the notation to one side, and let's focus on the abstractions. And for me, that's really what I'm more interested in here. I think having a common set of abstractions is much more useful than focusing on the notation. This might sound a bit crazy, but bear with me for a second. Let's go and get two maps of Krakow and lay them out side by side here on the stage. The two maps of Krakow will show the same things, won't they? Roads, tram lines, bus routes, the castle, the points of interest, the river. But the two maps might use different notations, different colors, different symbols, different types of lines. Same abstractions, differing notations. How do we decipher a map? There's a key on the corner. So the maps are essentially self-describing notations based upon a common set of abstractions. So let's take that concept and apply it to our software world. So how do I do this? For me, a software system is made up of a number of what I call containers. Right, this isn't Docker. A container is simply something that you can host code or data inside of. In real terms, this is a mobile application, a web application, a standalone application, a Windows service, a database, a file system, something like that. If I lift the lid on my containers contain components. For those of you who went to Anna and Bien's talk first thing this morning, it's the same concept. It's a component is a bunch of related stuff with an interface, a nice, clean public interface. Because I mostly deal with Java, my components are made up of classes. And we're done, that's it. System, bunch of containers, those things have components running inside them. My components are made up of classes. With this kind of set of abstractions in mind, you can then draw a bunch of really, really simple pictures. So you can start out with the big picture and draw a context diagram. So in other words, here's my system, and here's all the stuff around it. Do you remember during my quick introduction, I did the pinch to zoom in movement so you could see Jersey? It's the same thing. We take the system, we pinch to zoom, and we get to a diagram showing all the containers. In other words, this is the mobile app talking JSON to a web app talking JWC to a database, for example. We then pinch zoom into a particular container, show the components inside it, and if we really, really want to get down to that nitty-gritty detail, we can draw some class diagrams. So again, we've got some nice simple diagrams here to represent those common set of abstractions. Quick example for you, just to put this in context. As I said, I live in Jersey, and I built this site here, techtribes.je. It's a really super simple Java Spring MVC content aggregator. It basically lists local people, businesses, blog posts, tweets, and events that are happening in Jersey. This is my context diagram. My system in the middle with the monkey, my various types of users at the top, and my key system dependencies at the bottom. Nice and simple, sets the scene, nothing too scary from a tech perspective. For us as developers, we want more technical detail, so we pinch to zoom in on the monkey's head, and we get the containers diagram. Everything inside that red box I've just highlighted lives inside my system. That's what I am responsible for. This diagram also shows people at the top and systems at the bottom. And basically, the high-level architecture of my TechTribe system is this. There's an Apache Tomcat web application at the top. That's the point of access for all the users. There's a little standalone Java process at the bottom, which is the thing that reaches out to Twitter, GitHub blogs, and pulls the content back. And all of that content is being stored somewhere in those middle trio of boxes, right? So there's a MySQL database storing most of the entities. There's a MongoDB store on the other side for the tweets and blog posts. And there's a file system in the middle for the search indexes. And that's it. This diagram doesn't tell you anything about clustering or servers or deployment. That's a separate diagram. That's a separate view. If we do the pinch to zoom in movement on my content updater at the bottom, we get to see inside it. Same thing again. Everything inside that red box is inside my content updater. I'm also showing my external systems because my content of data talks to the outside world, and this content of data uses those other containers at the top. It's storing data in them. Nice simple diagram. Box in the middle is a Spring scheduled task, gets kicked off every 15 minutes. It uses the various connectors at the bottom and stores data using the components at the top. My diagrams tend to show simple boxes, names, technology choices, responsibilities. These diagrams are maps. These diagrams are maps that can help us navigate and explore and understand a large and complex software system. That's the whole purpose of them. Sometimes we want the zoomed out view of the world, and that's great for a certain audience. And us as developers, we want the zoomed in view of the world, components and technology choices. I'm not saying you should only draw these types of pictures, because there are lots of other ways that you might want to think about your software system. Wireframes and mock-ups and domain models and runtime and collaboration diagrams and deployment diagrams. There's a whole bunch of stuff you could use here. But what I'm trying to focus on is just the static structure. And it's a static structure from the system as a box down to containers, components, and classes. And once you understand that core static structure, it's really easy to weave a bunch of other stuff around it. So for example, if you want to create a deployment diagram, what's your deployment diagram showing? Well, it's showing how your containers map onto infrastructure, or Docker containers, for example. So ultimately, this all comes back to code. The static structure is classes down here, components, containers, system. So this is a static structure first approach. And the reason I do this is because I think the primary stakeholders of architecture, that's us. Software developers are the primary stakeholders for architecture. So here's an overloaded word I've used a few times. Adam also used it first thing this morning. I'm sure other people have also used this term during the conference. So let's define what a component means in the context of this stuff. Spring. I'm sure you'll know what Spring is, popular framework. There's Spring MVC, which is a great way to build web apps. There's a sample application called the Spring Pet Clinic, and it basically shows you, this is how you use Spring MVC, and these are the sorts of patterns that you can adopt. The diagram on the left here, I took from one of the slides that explains the architecture of the Spring Pet Clinic system. And it's your traditional layered architecture. So a bunch of browser stuff, HTML and CSS, number of Spring MVC controllers, some services, some data access objects. If you download the code to the Spring Pet Clinic system and throw it into your ID of choice, it looks like that on the right. There are a bunch of model classes, domains, entities. There are some JDBC implementation things. That's your data access objects, your repositories. There's a clinic service, which we'll come back to later. We got some utils because, well, why not? And we got some web controllers. So it's a really, really simple code base. Right, let's imagine that this is your system that you've now inherited. And you've never seen it before. What's the best way to get a handle on what this system looks like? That diagram on the left is kind of useful, but there's more stuff in the code. So let's try and get a better diagram to explain the architecture. Well, let's go back to the auto-generating thing. So why don't we just draw a UML class diagram of the code? Seems like a fairly easy thing to do. Most tools support this. That's what you get. Remember, this is only a small system. Imagine this is your 100,000 class system that you've just inherited. Now, I could have spent more than about 3 minutes trying to work out how to lay these boxes out properly so there were no overlapping lines. It's an impossible task. Don't bother. Is this diagram useful? It's just showing you stuff that was on the other side. It's showing you something about the relationships and the dependencies, but as an architecture diagram, is that useful? Not really. We can move the classes around into layers, but we're still going to have this overlapping line problem. Right, so let's start again. Why don't we filter what we show on the diagram? How do we do this? Well, instead of showing everything, why don't we show the structurally significant things and exclude the rest? So let's try this. Our entities and domain objects, do we think they are structurally significant? Maybe not. So I'm going to exclude those. My JDBC repository stuff, that sort of sounds structurally significant. I mean, it's in the architecture picture on the left as well. My clinic service, as we'll see, that's quite significantly structural. The utils, I hope, are not structurally significant, but we never know. And the web controllers, yeah, let's throw those into the picture as well. So if we take a much more filtered approach, we get something that looks more like that once you drag the boxes around. This is starting to resemble that layered diagram we saw before. So we've got the controllers at the top, the service in the middle, and all the repository implementations along the bottom. In order to show the correct dependencies, what I've had to do on this diagram is show you both the interface and the implementation class. So the interface basically lists out the operations and methods that this thing provides. The interface does not tell you what it depends on, what the implementation depends on. And once you throw the implementation classes into the mix, you can now see you've got this little tangle down in the bottom right corner. So this is still a much more useful diagram, but again, this is a small system. If this was your 100,000 classes, you're still going to get quite a big picture. Classes, what's the next level up? Components. How do we pinch zoom out one notch on the scale and create a component diagram of this system? In other words, how do we do something like that? So let's treat all of the controllers as components. Let's merge the interface and the implementation and call that a component as well. That seems a nice, sensible thing to do here, to remove some of that noise. Ultimately, I want to get a picture that looks like that. It's the same diagram, just drawn in a slightly different way. Controllers, service, repositories. So how do I draw this? And furthermore, how do I draw this automatically? So, do we want to merge the architecture and the code? Merge the code and the architecture. The thing I don't want to do here is go back to model-driven architecture of 10, 15 years ago. So for those not familiar with model-driven architecture, basically you'd buy a really big, expensive tool, and you would model the death out of your system. And you'd create 1 million different UML diagrams, and you'd annotate them with code and script and executable behavior and rules, and then you would press this magic button in the middle which said, build me my system. And pop, your system appears out of nowhere. And it all works beautifully, and the UI is gorgeous and everything. Every time you want to make a change to your system, guess what? You go back to that big, horrible, bloated modeling tool, you make some changes, you press the button, pop, your system emerges. It's a horrible idea. I'm definitely not going to suggest that. What I do want is that when I'm drawing these pictures, these diagrams, I want the abstractions to reflect the code. Because otherwise the diagrams are pointless, aren't they? If I have these diagrams on the wall and they don't reflect the code, what's the value in them? Now, I said this is not a new problem, and I've already referenced George Fairbanks' book, where he calls this the model code gap. Well, it turns out he's also got the answer. And the answer is very simply this. We should use an architecturally evident coding style. An architecturally evident coding style is basically dropping hints and metadata and information about your architectural intent into your code, so that things in your code reflect stuff on your model. In real terms, this is things like naming conventions. So if you're building a service or a component, make sure the name of a class or an interface or a package has the word component or service in it. This could be a convention whereby Much like Adam spoke about this morning, everything related to a single business component sits in a single Java package, having a nice one-to-one mapping between things there. This could be through the use of annotations, marking something at component or at service, stuff like that. Quick show of hands, who does this? Who consciously, explicitly does this? I'm going to say that's probably 10 or 20 people maximum. Wow. When you read this stuff, it sounds like such a sensible idea. Like, obviously we should do this. Yet we don't do it for some reason. Now, I showed you a component diagram for my Tech Tribe's content updater. So we can ask me this question. Does my diagram reflect the code? There was a component lurking in the top right corner called a tweets component, and all it does is it lets you get tweets from a Mongo database and push tweets into a Mongo database. So given that there's a box labeled tweet component on my diagram, can I find something in the code that looks like a tweet component, a single thing? And the answer is yes. Do you know why? Because I'm awesome. Thank you. Now, I'm joking about the awesome thing, because actually, it never started out that way. And there's an interesting little story here. And the reason that it actually didn't match in the first place, and that I'm not awesome, is because the first implementation of my tweets component was your traditional standard layered architecture. So I had a services package with all of my business services in, and I had a data access package with all of my data access objects in. There was a tweet service, and there was a MongoDB tweet data access object living in two separate packages. Where's my tweet component? It doesn't exist. My tweets component is really a kind of logical grouping of two things in two separate packages. It's a slice through a couple of layers. That's what my tweet component really is in reality. This is a really, really nice example of the model code gap in action. On my diagram, I've drawn one box. In the code, it's two boxes, really. How do I fix this? How do I make myself awesome? Two options. I either redraw my diagrams. That's way too much work, because now I've got twice as many boxes of my pictures. Or I refactor. And that's what I did. I did a really, really simple refactor. And what I do now is I do something called package by component. And this is my implementation of an architecturally evident coding style. And it's really, really simple. What I want to do is make every component sit in its own package. So my controllers, or my groups of controllers, they'll sit in a package. I can treat them as components. And I'm going to lump my service and my data access object together and call that logical grouping thing a component and stick it in one package. In real terms, this is now what it looks like on the right. So I've got a single package called tweet component. The interface has just been copied across. I've renamed it. Again, another architecturally evident coding style. It's now called tweet component. Fantastic, we can find that thing in the code. My default tweet service has now been renamed to something equally as horrible, but they say naming is hard, so whatever. And what I've done with that class is I've made it package protected. It's not public, it's package protected. So it can't be seen from the outside world unless you're cheating using reflection. And my MongoDB tweet DAO, I've copied across. Also package protected. So I've gone from a layered architecture to something that looks more like components. My component still has an internal layered architecture. I can still switch out Mongo for something else. But from the outside world, if you want access to tweets, you have to go through that public interface. That's kind of cool. Using Java's package protection thing to enforce some boundaries, some encapsulation. You'll notice my tweet DAO interface has sort of disappeared. You can't have non-public interfaces in Java. So I just deleted it. This is not a silver bullet. There are some implications and ramifications of doing this, which I'll talk about in a second. But this is now what the code looks like. So there's my interface. Standard Java interface. I've created my own annotation here, add component, and that's what it looks like in the code over here on the left. So my package has my interface, my implementation class, the data access object, and in this case, my Spring configuration. That's one approach. There are lots of other ways we can do architecture-driven encoding styles, so naming conventions, packaging conventions, annotations, attributes for any C# developers here. Maven modules, right? So if you've got 1,000 Maven modules, which I hope you don't, but if you do, maybe you treat each one of those Maven modules as a component. OSGI, module bundling system for Java. Again, maybe each OSGI module is a component. If anyone's seen the new Java 9 Jigsaw stuff, again, that's going to be a fantastic way to explicitly expose certain parts of a module. So we can use the Jigsaw stuff to create nice bounded components. I really like that. Microservices is actually an architecture-driven encoding style. If you have 20 different microservices, well, each one of those microservices is its own nice little black box with a nice clean public interface. If you were to draw that microservices architecture, what are you going to draw? 20 boxes. So again, it's about making these two worlds match up. Yeah, the ramifications of this approach. So of my approach is testing. So one of the things we like to do with layered architectures is mock stuff out. So if we think back to my previous implementation, I had my tweet service, which depended on my tweets data access object, and there was a Mongo implementation. Traditionally, what I would do to unit test the service is provide a mock implementation, an in-memory implementation of the data access object. Because I don't have an interface anymore, that's harder to do. There are some ways we can get around this. The other approach is to just not do unit testing. So this is the traditional testing pyramid thing. Loads of really fast-running unit tests. Bunch of quite fragile, brittle integration tests. They normally break, and you usually use @ignore to turn them off. Temporarily, of course. By temporarily, I mean forever. And then if you're really lucky, you get some UI system and functional tests on top. What's a unit? How big is a unit in a unit test? Is a unit a class, or a component, or a feature, or a piece of behavior? When we're writing integration tests, what are we integrating? Are we integrating classes? Are we integrating components? Are we integrating our code with the database? Unit and integration are just massively ambiguous terms. And this is one of the things I want to challenge, and I want you to go away and think about this some more. The approach I've taken now is I have a much more architecturally aligned testing pyramid. It doesn't look like a pyramid anymore either. I still want lots of low-level, I'm going to call them class tests. So this is where we test individual methods or individual classes, or maybe small collections of classes together. You know, super fast, mocking out stuff where needed. With my tweet component, what I actually do is I do none of that, and I just do a component test through the public interface. I spin up Mongo, I throw some stuff in behind the scenes, I run some tests. This allows me to get a really nice level of coverage with a really minimal amount of code. This works because I have access to Mongo, I own the whole stack, and it's super fast. If I'm accessing third-party services, if I'm accessing microservices, if I'm doing something asynchronous, this is a bit harder to do, so maybe you do want to revert to the class-level tests with mocking out boundaries, for example. And a bunch of system tests on top that test, end-to-end things through your system. The names match the stuff I talked about earlier. System, containers, components, classes. So what I'm trying to do is create a bunch of tests that test those things explicitly and be much more precise about the naming we're using here. I'm using this so far, it works really well for me. Have a think about it. So now we get to the title of this talk, Software Architecture as Code. The code is basically the embodiment of the architectural intent, isn't it? If we have nothing else but the code base reflects our ideas. It's the realization of those ideas. There's a really interesting question we can ask here, though. Does that code contain the architecture? Can we reverse engineer the architecture from an existing code base? This is from a paper from 1996, and it's a paper about architecture description languages. An architecture description language is simply, it's a bunch of text that you use to describe the structural elements of your system. There are a few out there, they're not massively used. One of them, by example, is called Darwin. In practice, architecture is embodied and recoverable from code. This was written in 1996. I don't think this is true anymore, given the languages and technologies that we're using. I've seen very few code bases where we can extract an architectural model from the code. I don't think it exists. So let's try this. Imagine we've got your system, and we want to draw some of those diagrams I talked about before. We'll start with the context picture. If I look at your code base, can I extract a list of all your user types? Maybe. So some teams have, an enum representing all their user types. If you're building a web app, maybe you've got some security configuration that maps roles to URL paths. So we could scrape that information and make an assumption about the different types of users. It's a bit hard to do reliably, though. What about systems? Can we get a list of system dependencies just by scraping a code base? It depends how you built your system. So we could look for specific types of jar files. For example, with my tech tribes example, I'm using Twitter for J. So we could therefore write a rule that says, if you see Twitter for J on the class path, make the assumption that this system uses Twitter. But we still don't know why. We could again scrape configuration files for known API endpoints. So if you see this particular endpoint, make the assumption we're talking to that system. What about those horrible situations where I'm building my system and I want to talk to your system, and what I'm going to do is drop a file on this file share and you can pick it up? These sort of weird implicit system integration points, how do you get that from a code base? I'm not sure you can. So that information is quite hard to find. Let's pinch to zoom in, containers. Can we get a list of the containers that make up your system just by looking at the code base? We could, so imagine that you've got an IntelliJ project file or an Eclipse project file, a workspace. You could scrape those files to find web apps. You could scrape those files to find examples of public static void main. If you're using Docker or Vagrant, you could scrape those artifacts as well to try and extract a list of things you think need to be running. Kind of hard to do, though. That information is not readily available in the code. Pinch to zoom in. What about the component diagram? Can we auto-generate a component diagram from our code? Yes, if we've used an architecturally evident coding style. In other words, we've dropped hints into our code base that somehow describe what a component looks like. So if that's the case, it's really, really trivial to write some rules to extract stuff from our code base. And this is really what I'm trying to do here. Given a code base, I want to extract as much information as I possibly can from the code base and supplement it with the stuff I just can't get readily from the code. And the way I've done this is by creating an architecture description language as Java code. So in other words, I'm going to write some Java code to describe my Java system. This might sound a bit crazy, but actually it offers you a bunch of opportunities that we've never seen before. So here's some example code for you. And this Java code I'm showing you now is some Java code to describe the architecture model for the Spring Pet Clinic system. The couple of lines at the top, the workspace and model, that's just some boilerplate. So we're going to create a workspace and we create a model to store all of this stuff in. What I'm then going to do is I'm going to create a software system. This is just a simple class library, simple Java class library. I'm going to create a software system, give it a name, the Spring Pet Clinic in this example, and I'm also going to create a person. If you read through the documentation for the Spring Pet Clinic system, basically it's a system for employees of a clinic to use and get information. So that's my one type of user. It's a clinic employee. And what I'm going to do is I'm going to wire them together. So I'm going to say clinic employee uses the Spring Pet Clinic system. Done. That's all the information we need to create a context diagram, because it's a nice, simple system. Pinch to zoom in, the containers. What does the containers bit look like? Well, essentially, it's a web app talking to a database. That's it. So again, I'm just going to model that in code. I'm going to create a container as a web app, give it some properties. Likewise with the database. And then I'm going to say the clinic employee, the user, uses the web app, and the web app uses the database. So again, I'm just wiring together these bits of the model. I don't want to have to do this for all of the components that make up my system. Since this is code, I can scrape that stuff from the code, though. And I can make some assumptions. So what I've got here is a component finder thing. And there are different strategies, and those different strategies have different rules. So I've got a Spring component finder, and basically all it does is it looks for the Spring annotations. @controller, @service, @repository. And it treats those things as components. So that's going to extract my controllers, my service, my repositories. It's also going to wire up the dependencies between these things. So we're going to get a nice, clean component model out of doing that. I said I want to extract as much useful information from the code as possible, so I'm also going to pull the Java doc, the class-level Java doc, and use that to populate the description for my components, because that seems a nice, simple thing to do. So that's going to give me this kind of amorphous blob of components. I then want to just put a bit of wiring top and bottom. So I'm going to say that the clinic employee uses the controllers. That's the top part of my picture. And I'm going to say that the repository uses the database. Again, it's code, nice and easy to do. So that's my model. I have a model of my software system now in memory. I need to visualize it, so I'm going to create some views. And these views correspond to the C4 diagrams I showed you before. The context, the container, the component diagrams. And it's really, really simple. We create a context view, which is all people and all software systems. Likewise with the container picture. And we're going to create a component diagram for the web app. What I'm also going to do is I'm going to link my components to the source files on GitHub. So what I want to do here is create a nice traceability between my components and actual code sitting somewhere. And I'll tell you why this is useful in a second. Right, so all of that stuff is all open source. It's called Structurizr for Java. It's on GitHub. You can download it, play with it. There's the Spring component finder strategy. There's a naming convention finder strategy. There's the JavaDoc stuff. I'm also doing a Java EE component finder strategy as well. That library allows you to build up a model. You can then export that model as JSON. Unless you guys can visualize JSON, we need something to visualize that for us. So this is the other piece of the puzzle. I built a simple web app. It's called Structurizr, and it basically takes these models and visualizes them for you. And these are the pictures you get from the model. So this is my context diagram for my Spring Pet Clinic system. It's a user using the system. Wow. But it's a simple system. Pinch to zoom in. This is my containers diagram. It's the user using the web app that talks to the database. Again, all of this stuff has come from the code you've just seen. And that is the diagram I showed you before. So that's the component diagram for the Spring Pet Clinic web application. It's extracted all the components automatically, it's wired them all together, and it's added that JavaDoc to create the descriptions for the components. In the tool, if you were to double-click one of those boxes, it takes you to the source file on GitHub. So now we've got this nice traceability from the software system down to the classes. As I said, I'm in the process of creating a Java EE approach, but because the framework's open source, you can create any strategy you want to extract and find the way that you think about components. Do you like this diagram? This is what happens when I threw my own tooling at my TechTribes web app. It generated this diagram by default. Now, I can explain this diagram, but I shouldn't have to. All of the stuff around the outside, those are my Spring MVC controllers, and all of the things in the middle are my package by components. And when I generated this picture, all of the controllers used a common set of components because they were showing common information on the page. But this is not a very useful diagram, so how do we fix this? Well, it's not Visio. It's not a static picture. It's a model. It's a dynamic model of a real code base. And because the model is described in code, guess what we can do? We can write more code to slice and dice the model. So we can do stuff like this. Go and find me every Spring controller and create one component view for that slice of the system. And the net result is very simply this. We get a larger number of much, much simpler pictures. So having this model as code provides you a nice bunch of opportunities. Throw this into your build system, guess what happens? You get continually updating software architecture models and diagrams. So again, we're trying to consciously and explicitly bridge this gap. So this is my whole goal here, to basically bring software architecture back down to earth and make it relevant to us as developers. So we can have much, much better conversations and understand architecture, essentially. What's the actual point of all of this? People tell me that their systems are hard to work with. If this is the case, if your code base is a pain to work with because it's messy, change it. Think about the architecture-level encoding styles. Think about doing the simple refactorings. Think about dropping metadata into your code base and cleaning up your code base. The maintainability of your system, I think, is inversely proportional to the amount of stuff you have, particularly public stuff. And I'm going to throw microservices into that mix as well. You've just got many more moving parts there. I think a good architecture enables agility as well. So if you want to build a system that you can change quickly and it responds to change, that's a quality that you need to engineer in. Agility is actually a non-functional requirement that we often kind of ignore. So yeah, treat it as a quality attribute. If you want an agile architecture, you have to create it. Otherwise, you get that horrible big ball of mud that it just takes forever to work with. Oh, and this is interesting because there are different ways we can build systems, of course. On the one hand, we've got the monolith, where we jam everything into that one big deployable package. And sometimes that turns into that horrible big ball of mud. But hey, we have tooling to support this. Refactoring's easy. Deployment's easy. We know how to build monoliths. On the other side, we have the service-based architectures. Microservices, for example. So rather than deploying one single thing, we deploy a whole bunch of things. And we can have them with different development life cycles, different technologies. This gives us lots of agility, lots of flexibility, lots of scalability. But it's a much more complex architecture to create in the first place. The thing I love about our industry is that it's either one of those or one of those, and there's nothing in between, except there is. Good old-fashioned component-based design. We can still create a small number of monoliths with nice, neat components inside them. What's wrong with that? Okay, it's not cool, it's not hipster, but we can still build nice, clean, maintainable code. And this is what my components are all about. It's about creating nice, modular, monolithic applications. And people can't do that. People find it really hard to create nicely structured monoliths. And then they say, well, what we'll do is we'll jump on microservices because that will force us to create nice, clean things. No, it won't. You need exactly the same design thinking to break your system into smaller parts. If you can't build a modular monolith, don't bother with microservices because it's just going to hurt. You're sticking networks in the way. The thing I like about components and modular monoliths is it's a really nice stepping stone to a microservices architecture. Those of you who went to Adam's talk first thing this morning, he said exactly the same thing. If you get your seams and your boundaries right in your monolith, you can kind of pull those things out, providing you're not accessing a single data store and you don't have lots of shared code, but you can kind of pop those into their own container and make them a microservice. If a microservices architecture solves problems you guys have. And again, that's something that Adam was talking about this morning. So my closing comments here are really think about how to align your software architecture model and how you think of your system at the big picture with the code. These two things should map really, really cleanly. Think about that architecturally evident coding style stuff. Try and get some of those characteristics and properties and approaches into your code base so your code base better reflects your architectural model. Stop making every class public. Right? This is the most concrete advice I think I could probably give you today. You've seen it. If we have a code base where everything is public, it's really easy to take shortcuts. I'm just going to call that thing there because it's public. I'm going to jump through the layers because it's public. I'm going to go back up the layers because stuff is public. This is really hard to do because lots of the tooling forces us to create public things by default. And also, it's muscle memory. How many times have you created a class in Eclipse or IntelliJ and it's public, or you've just unconsciously felt yourself typing public class? I have a challenge for you. And my challenge is very, very simple. Every time you type public class without thinking, 1 zloty goes to charity. This will stop you, or at least slow you down a little bit. If your architecture model is in the code, if your code reflects your architecture model, well, you can extract it from the code. And you can draw those nice, simple architecture diagrams that we saw. Without big, expensive tooling, without these horrible, horrible, messy diagrams. We can get diagrams that make sense. We can get diagrams that allow new joiners to look at the code base and understand the code base. And we can explain it to people. And we can see our module boundaries. And we can see where there are candidates to take components out and make them into microservices. So it's about cleaning up our code base and exposing, the nice, clean nature of our code base. And my final closing thought is just think. We're doing lots of cargo cult stuff at the moment in industry. Layered architectures is one. Unit and integration testing is another. Microservices is yet another thing. There are no right answers. There are no silver bullets. The stuff I presented here is not the one true way either. But what I wanted to do is just open your eyes that there are other options. We can take advantage of the language features. We can look forward to Java 9. But basically, let's just build better systems, cleaner systems, modules, components, boundaries, and that sort of thing. Thank you very much.